Hi, my name is Tamires Barbieri. I'm a master student at São Paulo University in Brazil. I will present the work KS-SIFT, a keyframe extraction method based on local features, developed by me and Rudinei Goulart. The video scene segmentation is still an open research field and presents many challenges. It is a more complex problem than frame or shot segmentation, due to the subjectivity of the scene concept and the semantics involved. Among the approaches to achieve scene segmentation, the most common ones are based on the clustering of related shots. To this process to be successful, it is necessary to properly represent a shot. But to use information of all frames in a shot usually results in a huge data volume. So, in order to obtain a compact representation, many works adopt keyframes, that are frames selected to represent the most relevant content of the shot. The majority of works in literature adopt one keyframe, for example, the short first or medium frame. But just one frame cannot be enough to capture the variety of content in a shot. Besides, with few exceptions, the works use color histograms to characterize the keyframes, what, despite having a low computational cost, tends to lead to low efficiency when applied on scene segmentation tasks. So, in this work, we propose a new keyframe extraction method based on local features. Local features can provide robust descriptors and are able to retain image semantics in a latent fashion. Besides, they have been poorly explored in the video keyframe extraction field. Among the visual local descriptors, we choose to use SIFT, since it is invariant against photometric, color, rotation, and scale changes. As discussed, local features can bring benefits as an alternative to describe keyframes. So, we will discuss some keyframe extraction methods based on local visual features found at state-of-the-art works. The first one is proposed by Baber. They adopt just one keyframe, defined as the shot medium frame, and then extract surface features from the selected keyframes. This approach has low computational cost, since a small fraction of frames is processed, but can be selected an image that doesn't represent the most relevant content of the shot. Scherge also used just one keyframe, but in this case defined as the frame with the highest number of points of interest in the shot. This approach considers the image content, but only one frame cannot be enough to represent the diverse content of some shots. Besides, the method is more computationally demanding, because it processes all shot frames. Tempo and Zaharia selected a variable number of keyframes per shot. They use a window size parameter n, and the first frame is selected n frames after a detected shot transition. To identify new keyframes, they analyze images located at integer multiplies of n, and verify if the visual dissimilarity between them and the keyframe set already extracted is significant. Then, irrelevant frames are discarded based on the number of key points obtained, and the final keyframes are described by SIFT features. It is possible to see that the current approaches have problems of representativeness and computational cost. So, we developed a new keyframe extraction method, the KS-SIFT, keyframe set SIFT, designed to deal with the problems identified in related works. The first step of the method is to build the keyframes candidate set, KCS. As we can see in the figure, the first frame included in the KCS is the shot first frame, to ensure that each shot will be represented by at least one frame. Then we adopt a windowing rule. We use a window of size n, and frames at positions n plus 1, 2n plus 1, 3n plus 1, and so on, are selected for later analysis. We define n as 25, based on the usual capturing and exhibition rate of movies. After this, we extract SIFT features from the frames in the KCS. The next step is to build the keyframe set, KS. The first frame included in the KS is the first one in the KCS. Then, each frame in the KCS is analyzed and inserted into the KS only if its number of points of interest is sufficiently different from the number of points of each frame already in the KS, as shown in the example. The reasoning is to avoid the inclusion of similar frames. If the first criterion fails, it means that the frame being analyzed has a number of points of interest similar to other frames in the KS, but it may be still different if there are few coincident points of interest between them, as illustrated in the example. So, we compute the number of matched points of interest between the analyzed frame and each one in the KS to decide if it will be or will be not included. The result of KS-SIFT is a set of keyframes representing each shot. Here we have an example of keyframes selected using KS-SIFT. It is possible to see that the frames have differences in semantics and represent different shot moments. To be possible to evaluate KS-SIFT in scene segmentation context, it is necessary to define a similarity measure. We use the one-to-one symmetric matching technique, the OOS, to identify matching feature vectors between two shot representations. This technique aims to optimize the matches and removes a large number of matches caused by noise. After using OOS, we have as similarity measure the number of matched feature vectors between two data sets. We also developed a naive automatic scene segmentation technique to evaluate keyframes extraction methods applied to this domain. The technique searches for values in the similarity measure. It is decoupled of the keyframe extraction method and doesn't present any heuristic, elaborated approach or filters to improve the results. This is important because it makes possible to fairly compare different keyframe extraction methods. In the developed technique, we only consider a value when the reduction and respective increase in the similarity measure value is significant, aiming to avoid a local minimum. So, the first step is to find the meaningful reduction and increase rate. As this value depends on the video features, we compute it instead of using a fixed threshold. For that, we identify all reduction values in the similarity measure, as shown in the example. Then, we calculate a typical reduction to the video by deleting the 10% higher and 10% lower values, as can be seen in the graphic, and computing the mean of the remaining ones. This is the minimum variation necessary to identify a value. The next step is to cover all similarity values and to verify if there is a reduction equal or higher than the rate previously determined, and a successive increase equal or higher than the same rate. If the conditions are true, a value is identified, representing a scene transition. In the experiments, we used 5 video segments from movies domain. We adopted the first 50 minutes, disregarding the opening effects. In the table, we can see the number of frames, shots, and scenes used for each movie segment. We compare our KS-SIFT method with 3 state-of-art approaches explained previously: Baber, Shirley, and Tapur and Zaharia. We adopt the following steps. First, we apply the strategy for keyframe extraction. Then, extract SIFT features from the selected frames. For similarity measure, we use the number of matched feature vectors, and the scene segmentation is performed using the technique developed. So, we can compare the impact of different keyframes extraction approaches in the results. This table presents the effectiveness results. It shows the average values obtained for precision, recall, and F1 measure, considering the 5 move segments. It is important to highlight that we are interested in evaluating the impact of keyframes extraction methods on the results of scene segmentation. It is not expected to have high values, since the scene segmentation technique used is naive. Analyzing the table, it is possible to note that the KS-SIFT performs better than the other approach, with F1 measure on average 5.7% higher. It is also possible to see that KS-SIFT achieves similar values for precision and recall, indicating that the method is well balanced. This is relevant because as important as to identify only corrected scene transitions is to guarantee that all scenes in the database are covered. We also analyze the processing times. In the table, the word keyframe means the total time expended to extract the keyframes and the SIFT feature vectors, and the word match indicates the time expended with the similarity measure. It is possible to see that the time necessary to extract keyframes is higher than the time expended with the similarity measure. One can see that the Barber approach is the less time consuming, but is also the simpler one and presents low effectiveness. The approach of Tepo and Zahaya also has low processing time. It is because they use color histograms in the selection process that are less time consuming, but they can't achieve high effectiveness rates. The shared approach presents the higher costs for processing. This can be explained by the keyframe extraction approach that processes all frames. But the effort is not reflected into effectiveness, since the F1 measure is low. Finally, we have our proposed KS-SIFT that has processing time close to the fastest method, being 16.4 times lower than shared approach. But in this case, the relative increase in processing time leads to better effectiveness rates. We presented the KS-SIFT, a new keyframe extraction method based on visual local features that presented superior effectiveness to 3 state-of-the-art approaches when applied on scene segmentation context, and processing times close to the fastest methods. For future work, we can investigate improvements using image processing techniques to filter the most important regions of each frame and apply feature extraction inside the segmented regions. We can also apply KS-SIFT in other contexts, like video summarization. Thank you for the attention, and if you have any doubts, please email me.